Euclid's Elements, Book 2, Proposition 13. In acute-angled triangles, the square on the side subtending the acute angle is less than the sum of the squares on the sides containing the acute angle by twice the rectangle contained by one of the sides about the acute angle, namely that on which the perpendicular falls, and the straight line cut off by the perpendicular within towards the acute angle. So we've got our acute triangle, and we will drop our perpendicular. A, B, and C. And by proposition 12, we know that BD is perpendicular to AC. And the acute angle we're going to talk about is angle A. So I'll say acute angle A. And our to prove, I'll write this up here. Our to prove is that the square on BC, so on the side subtending the acute angle, is less than the squares on the sides containing the acute angle, so less than the square on AB plus the square on AC by twice the rectangle contained by AC, the side on which the perpendicular falls, and the straight line cut off within between the perpendicular and the acute angle. So that'll be AC, rectangle AC, and DA. Proposition 7 of book 2, we know that straight line AC has been cut at random, so we can say that the squares on CA and AD equal the rectangle contained by twice the rectangle contained by CA and AD plus the square on the remaining segment DC. Now, using common notion number 2, we're going to add equals to equals. We're going to add the square on the perpendicular, the square on BD to both sides of step 2. So we'll get square on CA plus the square on AD plus the square on BD equals twice the rectangle contained by CAAD plus the square on DC plus the square on BD. And now we're going to apply proposition 47 to a couple of times. So proposition 47, we know that if we look at triangle ADB, which is a right triangle, we know that the square on AD and the square on BD are equal to the square on AB. So we can state that. And then applying Prop 47 to right triangle CDB, we know that the square on DC and the square on DB are equal to the square on BC. So we can write that. And I'll rewrite, step 5, we'll rewrite all of this. So now we have CA, square on CA, plus the square on AB, plus twice, or equal to twice the rectangle CA AD plus the square on BC. Which means if we subtract twice the rectangle CAAD, then we'll be left with the square on BC being less than the squares on CA and AB by exactly that amount, namely twice the rectangle contained by CAAD, which is what we're trying to prove right here, QED.